Two spheres of mass m and 3m are arranged as shown on this left side of the figure, and they're dropped from rest. The large sphere strikes the floor. That's the first of two back-to-back collisions. And when it strikes the floor, it just rebounds with the same speed that it hit the floor with. And immediately after, so now it's moving upward, then immediately after it hits the floor, the other small sphere, which is still moving downward at that same speed v, collides with the upward moving sphere. So we're going to assume that air resistance is negligible and solve for some of these things where we express all the answers in terms of the capital M, capital H, and any physical constants. So the first thing is, let's determine the speed with which the large sphere, or basically it's going to be the whole thing, ends up striking the floor. And this is really easy because this is just one single object. We're just looking at the large sphere just falling to the ground. So you can use conservation of energy or free fall kinematics. And most of you shouldn't have a trouble with this one, and you end up getting a final answer, no matter which method you use, of v is equal to the square root of 2gh. So I'm not going to go through all the details of that one, because I think you should be able to do that on your own. So this is where the first collision comes in now. So that sphere hits the ground with a speed of v, and it rebounds from the ground at the exact same speed v, but now it's heading upward. And that second sphere, the smaller sphere, is still moving downward at that same speed v. So now that second collision is when the upward moving large sphere strikes the smaller moving downward sphere. And what happens during that second collision is it says it causes the that large sphere to actually stop moving. So because it's a collision, we're going to set up conservation of momentum. So we have m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. The m1s represent the large sphere, so that everywhere we have an m1, I'm going to replace that with a 3m. Everywhere I have an m2, that's going to be the small sphere, which has a mass of big M. The velocities, the v1 initial, that is the speed of the velocities of the objects before the collision. So that would be v in the upward or positive direction for the 3m sphere, but negative v because it's in the downward direction for the smaller sphere. And then it did say that after the collision, the larger sphere, the 3m, or the mass 1, stops moving after that second collision. So that tells you that this term, m1, after the collision, is not moving, so that term is going to be 0. Alright, so let's get everything plugged in. So for m1 is 3m, and that's got an upward speed of v, plus m2, which is m, and that has a downward speed of v, so the velocity is negative v, is equal to, and then this last term over here, this again is the small sphere, so it is m, and that's moving with some unknown speed. So we're just going to call that, the problem defines it as vs, if we're doing part B, the expression for the speed of the small sphere immediately after the collision. So this stuff combined, this is basically 3mv plus negative mv, or 3mv minus mv, which is 2mv, is equal to mvs. We have a big M, which cancels out on both sides, and that tells you a very simple expression now, that vs is just equal to twice the initial speed. Vs is equal to 2 times v for answer C. Oh, sorry, for answer B. Part C, indicate whether the collision between the two spheres is elastic or inelastic. So if the two spheres had stuck together, we could automatically answer this question and say it's inelastic, because that's just an example of that's a perfectly inelastic collision. But when the two objects are not stuck together, Now it depends on if kinetic energy is conserved or not. So we actually have to calculate kinetic energy before and after the collision to see if it's conserved. And if we get the same exact thing before and after the collision, then it's elastic because it's conserved. And if we get two different answers for before and after, then it's not conserved. So before the collision, the initial kinetic energy is, and remember that's when we have mass 3m moving upward at speed v and mass m moving downward at speed v. So the initial kinetic energy of the whole thing is 1/2 times the larger mass, 3m, times v squared, plus we also have to do the kinetic energy of that smaller sphere, that's 1/2 times m, times, and that one also has a speed of v. Remember, kinetic energy is a scalar, so the direction of the velocity doesn't matter, so it's v squared. So we have 1/2 times 3, which is 3/2 mv squared, plus 1/2 mv squared. That is equal to 2 mv squared. That's the total kinetic energy before the collision. And now let's calculate the kinetic energy after the collision. So K final, and this one's going to be a little bit easier to do because remember, one of those objects after the collision is not moving. That larger object right there is not moving, so we only have to calculate the kinetic energy of that smaller mass. So the formula is 1/2 times that smaller mass, which is v, and now after the collision, that smaller mass was moving at a speed of 2v. So it's going to be the 2v that gets squared. So 2v squared. That leaves you with 1/2 times m. Now we have to square both the 2 and the v. So it's going to be 2 squared is 4 times v squared. And then you'll notice that this 1/2 cancels out with this 4 to leave you with a 2. So you get 2 m v squared. And look at this. The kinetic energy before is exactly the same as the kinetic energy after. So the kinetic energy was conserved, which means that this is an elastic collision. Remember, you can also call that perfectly elastic if you want to. They mean the exact same thing. Now, most collisions are inelastic. Some kinetic energy is lost. This is one of the few rare examples that turned out to be an elastic collision. But if you're ever in doubt and you just cannot figure it out, take the guess and say that it's an inelastic collision. In part D, let's determine the final height, which we're going to call little h, that the small sphere rises above its lowest position. Now we just have a sphere that is moving upward on its own. There's no collision happening here. It's just a sphere that starts off with a speed of 2v and moves up to some height, which we're trying to figure out. So we're just going to use the same thing we used back in part A. We can use either free fall kinematics or we can use conservation of energy. So let's just use, this time I'll use conservation of energy. So Ki plus Ui is equal to Kf plus Uf. When the sphere is first moving upward, it does have kinetic energy, but it does not have gravitational energy because it's at the ground level. So we'll say Ui is equal to 0. And then at the highest point, the kinetic energy goes to 0. Since it is no longer moving at the highest point, we just have gravitational energy. So K initial is equal to U final. We plug in the formulas. We have 1/2 m times the velocity. Remember, the speed was 2v squared is equal to the final height, or the final gravitational energy, which is mg little h. We have an m on both sides, which cancels out. And we have 1/2 times 2v squared, which is 1/2. The 2 and the v both get squared. That gives you the 4v squared is equal to GH. The 1/2 and the 4 combine to give you 2. So we have 2v squared is equal to g times, and I just realized that that is actually supposed to be a little h in the previous thing, not a big H. So 2v squared equals gh, but it says it wants to get that height in terms of the original height. So if we go way back to the beginning of the problem, we calculated this. The v is equal to the square root of 2gh, which has the original height, capital H, in it. So if I take that v squared and replace it with v squared is equal to 2gh, this is the missing step that will help simplify the problem. So we have a 2 times that v squared, which is 2g big H, is equal to g times little h. We have a g on both sides, which cancels out. And what we're left with is 4 big H is equal to little h. And what that should tell you then is that the final height of the small sphere is 4 times the original height that it was dropped from.